All right, awesome. Okay, so what we are going to talk about is properties of exponents. So this, again, should be review, but a good review because we're going to be doing a lot with exponents. And if you notice when you have your notes, it's kind of a really quick, easy chapter. Well, at least what we're going to cover in it. So we just have 5-1 and we have 5-2 and 5-3. And then that's it. And then chapter 6 is also 3 little sections. So we kind of just combine those together. But a lot of what we're going to be doing is review. So that's a good way to come back, not having to like jump into anything crazy like, deriving imaginary numbers or anything like that. We're just going to review some things that you've Algebra 1 just to make sure we have a solid base, and then do a couple of different functions with it, but pretty easy stuff. All right, so here we have a little chart, properties of exponents. I think it's just helpful to review kind of exponents in general, and we'll just kind of go down the list. So an exponent, just to remind everybody, even if you're listening, is the little number that's up in the air here. This is your exponent. So that's what we're dealing with. All these exponential expressions. Okay, so I actually don't even have what the technical name of the property is. So I should probably have that listed on here. This chart is missing that, but we'll kind of talk about each one. So this first property is what I like to think of as kind of the distributive property of exponents. So what I mean by that is if you have, well, you can see here, if you have x times y inside the parentheses to the power of m, then you can distribute that exponent to everything that's inside your parentheses. So I think it's pretty obvious there, but if you, and there's an example here, if we have x, y to the third, that's the same as x to the third, y to the third. Another way to think about this is like if you would have 3x to the, let's just say second power, we'll make it easy. We want to make sure that when you're getting rid of your parentheses, you're distributing the exponent. And so that's going to go to both terms. So it's going to become 3 squared x squared or 9x squared. So I think you probably remember this, Connor, and people that are listening later, you probably remember this. I think the thing that tricks people up sometimes is they want to forget that number there also gets applied to the exponent. So don't forget about the lonely number. It wants to have the exponent too. Okay. The second one is just like the first property. It's the distributive property, but it's for numbers that are written as a fraction. But same deal works. So if I have, for example, 5 over y to the third power, means it's 5 to the third power over y to the third power. So these parentheses are basically like your gatekeeper to whatever's inside. And this exponent applies to everything that's inside the parentheses. So if you did, for example, 5x over z, well, yeah, we'll just leave it like that, to the second power. That second power is going to apply to everything inside the parentheses. So it's going to be 5 squared, x squared, z squared. And then you can evaluate 5 squared is 25. But that's what's going on with that. All right. So again, I think you probably, have you seen these, Connor, before? Probably have seen all these. But a good review of kind of where we're at. All right. It's in there somewhere. All right. And this chart, use the chart, right? Nothing wrong with using the chart when you're trying to remember them all. Okay. This one is one we've been doing for a while. This is when you have the same base. That's not what I was trying to write. Okay. So we have x squared times x to the fifth. Okay. And in order to combine two terms, so we have the same base, right? We share x. We have the same base, and if we want to be able to combine them, we're allowed to do that as long as we have the same base. And we do that by adding the exponents together. So this is x to the 2 plus 5, or x to the 7th. Okay, so that's the one to remember. If you completely forget sometime, or you're like somewhere and you're like, oh man, I completely forget, you can just write it out. Like, so, I mean, it's not very fun to do, but x squared is x times x, right? And x to the 5th is x times x times x times x times x. A lot of x's. And so if you think about this, this is just a big multiplication problem. This is the definition of what an exponent is, right? X squared is 2x's, and x to the 5th is 5x's multiplied together. So now we have a total of 7x's. So x to the 7th power. Okay, so that's when we multiply. Dividing is even easier if you forget. So if I have, for example, x to the 5th over x to the 3rd. So when you have, again, the same base and you're dividing, when you multiply, you add. So when you divide, you subtract. So this is going to be x to the 5 minus 3 power, or x squared. I actually think division is a little bit easier because, excuse me. Sorry about that. I think it's a little bit easier because if you really think about writing this out, this is x times x times x times x times x. 5 x's on the top, 3 x's on the bottom. You get to do a lot of crossing off, and you're left over with 2 x's on the top. Okay. So that is that. All right, so now, this is the one that confuses people. When I have two exponents that are being multiplied together like this, I add them together, right? But what happens, next case, it's kind of a mess on here, but it's on here. What happens when you have, I need some room. What happens if you have a power to a power? So let's try to squeeze this in here. So if I have x cubed to the 2nd power. So x cubed to the 2nd power. So you have a power to a power. So what happens when I have that? You might be tempted to add them together just like we did over here, but this is a different problem. This is just basically the same base being multiplied together multiple times, right? Over here, we have a power raised to a power. So really what we're doing is we're doing x to the cubed times x to the cubed, because that's what this square means, right? We're multiplying this inside here twice. No, I should have written the cube there. X cubed times x cubed is really what we're doing. 2 times, right? And then if I go back to my rule, if I have x cubed times x cubed, that's x to the 6th power. So when you have an exponent to an exponent, you actually multiply the exponents together. So if I had x to the 7th to the 3rd power, then I'm going to multiply these exponents together to get x to the 21st power. Or I could think of it as x to the 7th times x to the 7th times x to the 7th, and 7 plus 7 plus 7 is 21. You end up right back at the same spot. All right, so those are the big guys. Those are the ones that we use a lot. Let's clear this off. There are a few other ones that we want to talk about. Easy ones. We like these. These are like, what do you get when you multiply by 0? So any number to the 0 power is 1. So you can see this lovely example that they did. 473,837,843 to the 0 power is just 1. So any number raised to the 0 power is 1. Doesn't matter what it is. Okay? Any number that's raised to the first power is just that number. So because you're just multiplying it one time, right? So 5 to the first power is just 5. 400, I don't even know where this number came from, but they really like it. 473 million, whatever that is, raised to the first power is just 473 million. So those are two easy ones. Again, if you forget them, your calculator will tell you, but they're pretty easy peasy, right? And then the last one kind of works in conjunction with all these other ones up here. And this one's actually a really helpful one, and we use it a lot. And I think it's one that doesn't get covered as much in like Algebra 1. So might be new, maybe you've seen it before, but it is this property here. So if we have x, let's say x to the negative 2 power. So you have a negative exponent, right? That's the same as 1 over x to the positive 2 power. So this is actually a super useful one, so you can get rid of negative exponents. And it's kind of written right here. Well, it is written right here. 1 over x to the m power equals x to the negative m power. It also works if you would end up with 1 over, let's say, y to the negative third power in the denominator. We could write that as y to the positive third power. So this one is a really useful one. Again, I don't think it's as covered as much. But it's powerful in that we can move things from the numerator to the denominator, deal with negative exponents, and that type of thing. All right. So what do you think, Connor? Have you seen some of this before? Yep. All right. So now we're going to dig in and we're going to do some problems with exponents because that sounds fun, right? Oh, I don't have too many examples here. Okay. So maybe Connor and whoever is, when you listen on YouTube, try these first before you just see what I'm doing here. So we have 4 to the negative 2 power raised to the third power. All right, so I'm going to give you 1 minute to try it, Connor, and then I'll start writing it. And if you want to type it in the chat, you can, but if not, that's all right too. All right, Connor got it right on the chat. I don't think you guys can see it, but maybe you can. I don't know. On YouTube. All right, so we have 4, and that's right, Connor, 4 to the negative 2 power to the third power. So this is a case where we have an exponent raised to an exponent. So what we're going to do is we're going to multiply the exponents together. So we were going to do 4, and that's going to be negative 2 times 3. So 4 to the negative 6th power. Now, technically, and I don't know this, but technically in your book, you might actually not see this. How picky they are. I mean, this isn't like bad math, you know, like writing, I don't know, a fraction over a fraction over a fraction. But you might also see this written as 1 over 4 to the positive 6th power. They're both the same. Same way of writing the expression. If, for example, a math book asked you to write to simplify this without, simplify the expression without negative signs, then this would be the more correct answer. This is also correct. Okay, so number 2, you can go ahead and try it, Connor, if you want. Number 2, we have 2 2/3 to the -5th times 2/3 to the 4th. Okay, so what I know, and I should have actually mentioned this before, in order to do any of these exponents, the base has to be the same. So if this was, and I'm going to erase this, but if this was 2/3 to the -5th power times 1/3 to the -5th power, that second 2 is a 1, then it's a no-go. You can't use the exponent rules. Those two bases have to be the same. So in all these cases, they're giving you ones that are the same, but in this particular case, or I just wanted to mention that if for some reason you come across one and they have different bases, then no go. All right, so we do have the same base and we have two exponents and they're being multiplied together. So we're going to use, we're going to be able to add these two exponents together, right? So we have 2/3 and we have -5 plus +4. So we end up with -1. All right, so technically that's correct. That's the same evaluation of that. But again, we're going to kind of take it even further. And when we have a negative exponent, we're going to try to put it into the form where it's positive. So another way that I could write this is 1/2/3 to the positive first power, right? Because of that negative, we just flip it from the numerator to the denominator. Now this is not so pretty math. It's kind of ugh, right? So 1/2/3, we can kind of get rid of the 1, is the same as 3/2. So then if you actually use your calculator and you want to double check that you got everything right, or you would just want to have a sine curve, right? Let's see here. 2/3 to the -5th times 2/3 to the 4th. There we go. You end up with 1.5, which is 3/2. So your calculator will back you up. Unfortunately, you can't just write 1.5. We need to know the steps how to get there, right? Okay, so 2 more examples here. We have number 3 has 5 in the parentheses. We have 5 times s to the -2 times t to the 4th to the -3rd power. So Connor, if you want to start trying that, I'm going to clear off my screen here. Let's see what you get. And whoever's listening on YouTube, try it out before you just skip to the answer. All right, Connor's got an answer in the chat. This looks good. Let's see what we end up with here. 5s to the -2, t to the 4th, -3. Okay. So what we want to do first is let's get rid of the parentheses first, okay? So we're going to get rid of the parentheses by distributing this to the -3rd power to everything that's inside my equation. So this is where you're kind of using more than one property together, right? So we have this -3 applies, the exponent of -3 applies to everything that's inside there, inside the parentheses. So we're going to distribute the -3 to everything inside there. So we're going to end up with 5 to the -3rd power times s, and it's to the -2 power raised to the -3 power. And then we've got t to the 4th power raised to the -3rd power. All right, so that's what Connor had. Nice job, Connor. well, he simplified it a little bit. So let's do a little bit of work. So 5 to the negative third power. We could also write that as 5 to the positive third power, right? If we want to get rid of exponents, right? We have, this is an s to the negative 2 to the negative 3. So I need to multiply these together. Negative 2 times negative 3 is positive 6. So this is s to the 6th power, and that's in the numerator, right? And then I have t to the 4th to the negative 3rd. So I could write this as t to the negative 12th or 1 over t to the 12th power. Right, so then if I pull all this together, I end up in the numerator, I have s to the 6th, and the denominator 5 cubed is 125 t to the 12th. So this probably is the most likely way that you would see it written in your book if you want to look at the solutions. If you wrote it as 5 to the negative 3rd, s to the 6th, t to the negative 12th, that would also be correct. That'd also be a similar solution. Or not similar. It would be the same solution. Just two ways of writing the same thing. So I just want to let you know, too, when you get to your homework and you're maybe looking to check it, it might not actually look exactly the same based on how they place the numerator and or how they place the exponents with the negative numbers. All right, one more. You can try this one out ahead of time too, Connor, because I think you're getting them. All right, so we've got this one that has a that's a fraction, right? So we have 4r to the 4th, s to the 5th, divided by 24r to the 4th, s to the negative 5th. So what I like to do when I have fractions like this, let's pick a new color, is I actually like to kind of break the fraction apart. Because we're multiplying everything, there's no addition, we can break it up. So I can do 4 over 24 times r to the 4th over r to the 4th times s to the 5th over s to the negative 5th. And I apologize because my s's and my 5s and everything was looking very similar. Okay, so first we have a fraction 4 over 24. That's the same as 1 over 6, right? R to the 4th over R to the 4th just cancels each other out. Easy peasy. And I have s to the 5th divided by s to the negative 5th. So there's a couple ways that you can do this one. I know everybody loves when there's more than one option, right? One option is that I could say, well, I know that this s to the negative 5th is the same as s to the positive 5th. So another way to think about this is s to the 5th times s to the 5th, or s to the 10th. That's one option. Another option is, oh, I know that when I am dividing two exponents, I subtract them. So this is s to the 5th minus negative 5. And 5 minus a negative 5 is 10. So this is s to the 10th. So those are the two ways that you could end up doing that. So basically, this last term we know ends up being s to the 10th. So 1/6 times s to the 10th is how you'd simplify this guy up here. All right. So it's just basically a warm up back to using all those. I would highly recommend go through all the problems or go through part of the problems, check your work, make sure you're on the right track, finish them up. But just definitely go back and check. So if there are ones that you end up with incorrect, you can kind of say, oh, yeah, I got to remember that rule. It's kind of a good review session for that. All right. And just it's 3 through 13 odd and 25 through 35 odd. So you don't have to do all of 3 through 13. And I'm just looking at the last section if we want to. I'm just looking at 5.2. I think maybe we want to skip over 5.2. I'm not sure if we're going to do 5.2, but no. I think we'll go ahead and do 5.3 today. So let's just do 5.1 and 5.3, and then I'll send you on your way. Okay, so 5.3 is actually just a continuation of 5.1, and it's also stuff that we've already done before. So that's the good news for that. All right. So 5.3, when this opens up for me. 5.3 is add, subtract, and multiply polynomials. So this is, I guess it's not, it kind of uses the rules that we have before, and then a couple other things. So this is something we've been doing for a long time. You've done it in Algebra 1. Again, it's review. Homework is 3 through 21 odd, so pretty easy, homework section, especially when you see what it is. So what we're talking about is polynomials. So polynomial just means we have a set of terms that are being added or subtracted together, and we're actually adding and subtracting polynomials together. So this is a process of gathering like terms. I get excited about this, about why we can do it, because it uses one of my favorite properties, but you probably don't even care why we have to use it. But anyway, long story short, we're basically going to add these two polynomials together. Okay. And so what you have to do in order to be able to add or subtract polynomials is that you need to combine like terms together. So what I mean by like term is, in this particular one, t squared is a like term, okay, because we have two like terms that are t squared. So we have a t squared here and a 5t squared here. And because they share the same base and exponent, they both share t squared, then we can combine them together. They're like terms. I cannot combine together, however, t squared and 6t. And again, you guys know this already. I know we covered it in Algebra 1, but this is like review so that we don't forget our Algebra 1 rules, okay? So what I mean is and I think you guys know this, it's like intuitive, like, I know I can do that. We're allowed to add together t squared and 5t squared to make squared, because they share the like term of t squared. We're also allowed to add together, different color here, we're allowed to add together negative 6t and negative t to make negative 7t, because they both share the like term of just t. And then lastly, we're allowed to add together negative 2, and I think that's positive 8, because those are just our constant numbers, right? They're just numbers. And we get plus 6. So I think that's pretty easy. You guys have been doing this for a while. We combine the like terms together. Here's my 30-second why we can do it. So we can add together t squared plus 5t squared. We could add these together because of our like terms. And this actually has to do with the distributive property. It's one of the benefits of the distributive property. Let's actually add a 2 on here just to make it more interesting. So both of these terms share t squared, right? If we pull out our t squared, we're left over with 2 plus 5, which is 7t squared. So you know that 2t squared plus 5t squared is 7t squared. You just know it. But the reason that you can do it is because they have these like terms. You can pull them out with the distributive property, and that's why you can do it. So I think it's just a good reminder. That's why. But it's one of those things you just kind of know to do. Know why you're allowed to do it? Yeah. Oh, good. So, and that's how you can think about anything, why you're allowed to combine them. Because if you pull them out, whatever's left over is what you're combining together. It's not just mathematicians say so. Good. All right. It gets a little bit more complicated when you're subtracting. And that is only because the only thing that's complicated about it is that you have to remember, like in example 2, when you're subtracting everything that's inside these parentheses. So that's what trips people up. Everything else is the like terms thing. Once you see it, it's like, okay, I can do that. But you just have to remember that this subtraction applies to everything in there and inside the parentheses. So if I were to rewrite this, 8D, everything to the left of the subtraction stays the same. 8D minus 3 plus 9D cubed. That all stays the same, right? Then when I go to subtract, I need to remember to subtract every single thing that's in here. So people are usually good with the, I'm going to subtract D cubed. Okay. But I also have to subtract negative 13D squared. So I'm subtracting negative 13D squared. And I also have to subtract negative 4. So I'm subtracting negative 4. So I run out of room here. Oh, just make my paper bigger. Negative 4. I'm subtracting negative 4. Sorry for the bad writing. Okay. So if I simplify a little bit, 8D minus 3 plus 9D cubed. I can just keep minus 9D cubed. Subtracting a negative 13D squared was the same as adding 13D squared. And subtracting a negative 4 is the same as adding 4. So now I just go with my like terms. And you might have done this technique before, but you can actually underline, like those are my D cubes. I only have 1D squared. I have 1D that's by itself, and then I have 2 constants. So basically the ones that are underlined the same number of times are the ones you can combine together that are like terms. So 9D cubed minus 9D cubed is 8D cubed. So we'll start with the highest order. And then can't do anything to 13D squared. Can't do anything with 8D. And negative 3 plus positive 4 is positive 1. So it's not hard. It's just kind of make sure that you get all of those negatives in there. Okay, so Connor, why don't you try number 3? If you're listening, try number 3. I'm going to start writing it out. It'll probably take me just as long to write it out as you to do it. All right, so I'm going to start writing the second half of this equation. And because I'm subtracting, I have to remember to subtract everything in the second half. So that means I'm subtracting 3v cubed. And I'm subtracting a negative 12v squared. So a minus is plus 12v squared. And I'm subtracting 8v. Okay, so once I've distributed my subtraction, then I can get rid of my parentheses and I can start adding and subtracting things together. So it looks like the highest order that I have is a v to the fourth power. So there's one v to the fourth power there. I have one v to the third power. I have two v squareds. I feel like I should have the number of lines that's the square. I feel like it's kind of weird. I have two just plain v's. And you don't have to do this line technique. I'm just doing it to be really visual. And then I have one lonely little constant there, right? So now when I go to combine, I say, okay, I only have one v to the fourth. So 8v to the fourth. Okay. And I only have, I'm done with that. I only have one v cubed. So minus 3v cubed. Got that one. Now I have v squared. I have negative 2v squared plus positive 12v squared. So that's 10v squared. Then I have positive 8 plus positive v plus negative 8v. So that's negative 7v minus 4. And that's as simple as I can get. So sometimes when people do these problems, they get super nervous that that's really long and they want to combine some things. After they've done that, they're like, oh, now I just want to combine some more stuff together. But you can't combine together, again, because that, the idea that you can only combine like terms, none of the terms we have left are like anymore. They all contain v, but they're different powers of v. So they're not like terms anymore. Now, if for some reason, this is taking a little further, but if for some reason this negative 4 wasn't here, we could pull a v out of all of these and multiply it, but it really doesn't simplify it at all. All right, so I think that's good for today. Maybe when we come back, so next Thursday we'll have class 2, Connor, and I'll send out the email to everybody to remind them again. We'll finish up 5-3. It's a really easy section. You might even be able to finish it up if you have time. But it'll be a good place to just kind of remind everybody again too. So that's it for today. Good luck this weekend. Let me turn this off. Are you swimming a lot of events?